Hello, ladies and gentlemen, and welcome back. Root Beer here, looking at question C3, the second last question on our 2018 open paper. Consider a convex quadrilateral, ABCD. Let rays BA and CD intersect at E. Rays DA and CB intersect at F. I'm going to have to draw a picture here before I keep going. So let's say A, B, C. It's just a quadrilateral. So A, B, C. Oh, no, it should be numbered clockwise. So they said BA and what was it? BA and CD intersect. So I guess we have to make this a bit more slanted. So they intersect at E. And then DA and CB intersect at F. So DA, CB, I guess goes up here to F. I might redraw this picture, but I'm really just trying to understand exactly what's going on. Okay, so there's E and F as they have them named. And then we can keep reading. Diagonals AC and BD intersect at G. And then we're told that DBF and DBE have the same area. So let's put this diagonal intersection G here. And what was it? DBE is red triangle, and DBF have the same area. So that's what we're told so far. Again, we might redraw this picture. I'm going to redraw this red line here. Okay, so that's true for my quadrilateral ABCD. And then what are we asked? We're asked a few things, all relating to this original construction. You can read them all together, or you can read them one at a time. It entirely depends on you. I'm just going to read A part here. Prove that EF and BD are parallel. So what do we want? Let's use green. So EF, which I'm having trouble drawing. We want EF and BD. Oh, so the common base of the triangles needs to be parallel. So yeah, actually, if I redraw the picture slightly, it was E up here, F up here, and I consider B or DB as the base here. If I were to extend it outwards, we can drop from F and E some perpendiculars, some heights. But DB is the base. Let's put A here and G here and C here. But so DB is the common base. So if they have the same base and the same area, they must have the same height. So you could say something like drop perpendiculars from E and F to the extended line DB, since DB equals the base and both triangles have same area, these heights are equal. Now, how does this help me? Well, this tells me that F, the closest F can get to DB is H. Perpendicular distance is the shortest distance from my point to a line. But this other height, H over here, is the distance from E to D. So EF as a line can be seen to always be distance H away. Well, that's what it means to be parallel, is that these lines never get any closer. Right, so we can just sort of wrap that up. We can say, so line EF is always H away from BD. Now, for a moment here, think about it. Just because I know 2 points on my line are a distance H away, how do I know the whole thing is distance H away? Imagine I had another point that was slightly closer. That line would have to dip closer and then move away. That's not a single line. It could be some sort of curve, but not a line. So that's how we can say it. And if you want to, you can add that in. I think it's clear. So EF is parallel to BD as they're asking for. Because we've got those two equal triangle areas and BD happens to be the common base. Okay. B, prove that G is the midpoint of BD. So we know it's the intersection of the diagonals, but we want to show it's the midpoint. Okay. So what can we do, and will we be using this parallel line? Well, actually, with the fact that we've proved that these are parallel lines, I'm actually going to redraw the picture here as a triangle. So it was C at the bottom, then it was E over here and F over here. And say B to C goes here, or B to E goes here, D to F here. BD is parallel, so what we're going to have are two similar triangles here. Kind of nifty. A is here. Parallel, parallel. And G is right here. And I want to show that G is the midpoint of BD. So I need to show that this length is the same as this length. How can we possibly do that? Well, just based on my picture here, it looks like this triangle and this triangle might be similar. Maybe CGA splits BDA in half. So if they were similar, what would we need? We'd need the same angle here. We'd need the same angle. Well, that can't be true. Well, it could be true if it was 90 degrees, but that's a bit more of an ask. Because we got the intersectional line, I know opposite angles in the intersection are equal. So I can say that these, the green angles and the blue angles, are equal. So maybe not going for similar congruent triangles there will help. But I can say something like, so based on our picture, we could at least say triangle CBD is similar to triangle CFE. Now, how do you know that? Well, I would say it's clear from the parallel lines, but if you want to, you can say, well, the bottom parallel line intersects at this angle. Parallel lines intersect the same line at the same angle. So you can very easily show that, and then they've got this common angle up at the apex. And I think that's a perfectly fine thing. I don't think it's necessary to say. I mean, you're doing C3. You can act a little smarter. You can drop a little less of the obvious stuff, or drop a little more of the obvious stuff from your explanations. So we've got that. So that's similar. Does it help me? Well, actually, let's keep those angles in here just in case. Just while I've got the blue and the green ones up there. Now, of course, this picture that we've got here could be pretty common. What else do we know? We know that this pink triangle has the same area as this orange triangle. But they actually have ABD in common, so I can also say triangle ABF has area triangle DBF minus triangle ABD. But that's the same as, because we know that DBE has the same area. And it's also got ABD in it. So it's the same, it got the same area as this triangle over here, ADE. So that's kind of nifty, so we could add that in. This pink triangle must be the same as this, let's say, forest green triangle. And we could actually combine that. We could add in this triangle down here to the pink one, and add the same triangle into the green one and make some big triangles that are also equal in area. So that's kind of nifty. So we've got a lot of equal areas going on. Equal areas makes me think maybe we could do some sort of congruent triangle thing. I'm not entirely sure. But we're sort of getting away from BGD. It'd be really nice if I could do something with BGD. But I'm not entirely sure what. Now the pink triangle and the green triangle, they are the same area. So what could we do? And what could we do to try and get back to the big triangle? Well, I suppose to each one we could add this quadrilateral ABCD, and that would make a bigger triangle that would have the same area, but I don't know as that's necessarily helpful. It'd be more interesting if we could add this triangle to the pink triangle and this triangle to the green triangle, and that sort of gets us talking about G, but now we're sort of splitting things off on the same side. But I don't know if these two triangles are equal in area. Okay, so what if we were going to talk maybe about this big cyan triangle and maybe this big orange triangle here? What could we do? Well, I suppose inside here we could drop inside the pink triangle. We could drop a height. It doesn't necessarily have to go to the pink triangle. For example, I'm going to drop a height from A to CE as well, and it doesn't necessarily have to stay within the green triangle. Now, unlike the last part where we had the heights here, I can't say that these heights are the same just because of the same area, because we don't have a common base. We don't have a common base, sadly. But we could get a ratio, and then that ratio, because you'll notice that this is also a height for the cyan triangle and the orange triangle. And so this maybe allows me to transition from triangles whose areas I do know to a bigger triangle that's a little closer, or to two other triangles that are a little closer to the G that I want to talk about. Because right now I'm playing around with equal areas in the lower part of the triangle. I need to get up into ABCD. So if that's the case, we call this maybe H and this point I. So place H on CF, I on CE. Actually, I think for lettering purposes, I'm going to switch those around. I like when the order in the alphabet works out. So we'll call this H, this I. Perpendicular. So then triangle ABF has an area of 1/2 BF times AI, but this is the same area as triangle ADE, which is 1/2 DE times AH. Okay. So that's a nice relationship. That's sort of a nice fixed ratio here. We could rearrange this, I suppose, if we wanted to. Is that the best idea? BFDE, these are sort of the extensions for this triangle, or this sort of similarity. So they should be similar to... Oh, I can show that this triangle and this triangle have the same area, I think. So, hold on. Let's just look at a bare bones example. If I've got two parallel lines, I know that this triangle and the big triangle are similar. So we'll use the same letters, D and E, B and F. Right, that is the order, right? Yep. then we can say CD is to CE as CB is to BF, and that's some constant ratio R. Let's order it the other way. And also get it right. CE over CD is CF over CB, which is R. But also, CE is the same as CD plus DE. So CD plus DE over CD is the same as CF, which is CB plus BF over CB. So R minus 1 is the same as, I'm just getting rid of the CD and the CB here, DE over CD BF over CB. So these have the same ratio. So what can we say? We could say DE is R minus 1 CD, and also BF is R minus 1 CB. Now, how does this help me over here? Well, I've got BF and I've got DE. I can replace them with the bases for these smaller triangles here, and they have the same height because it's all going to the same line, CE or CF. So 1/2 R minus 1, which one was it? CD. And that went with A H, because that was with E, right? Yeah, AH is the same as 1/2 R minus 1 CB, replacing the BF with CB, and the other one's AI. So the area of triangle CAD is 1/2 CD times AH, which, just dividing through the R minus 1s, is 1/2 CB times AI. But this is the area of CAB. Okay. So what has that managed to do? Let's draw our picture again, but a little bit bigger. And we'll focus in on G, because we're actually up in the sort of G area. So let's give ourselves a bit more space here. So there's A. Here's C. I mean, that's going to be a little too perfect for what I want to draw. So let's say, no, that's not going to work. Let's make it a little less nice. We'll make it a little more slanted. So there's A, connected up. There's G. This is B, this is D, this is C. This one was E, this one was F, and down here we're in A. But now I know that this triangle is the same as this triangle, and so we can actually use almost, this is kind of cool, it's the same trick we did in the first bit. We've got a common base of CA. So if I drop some perpendiculars down so from B, I guess we could sort of squeeze it in here. D, we can sort of squeeze it in here. I'll get that these have to be the same height. And the angles that I pointed out earlier, that this angle and this angle are the same, and this angle and this angle are the same, that's enough to show that these are similar triangles that have a common length. They must be congruent. And so the hypotenuses are the same length. That's okay. All right, we can write that up. So, where are we in terms of letters? HI, so we could call this this one J, and this one K. So use common base CA. All right, it's common to both of these triangles. Drop G and K perpendicular to CA from BK as shown. Same base plus same area means same heights. So DK in length is the same as BJ. Notice angle DGK is the same as angle BGJ. So these triangles are similar. But since we just showed DK has the same length as BJ, in fact, we have that DGK is congruent to BGJ. So DG is equal to BG because they are the hypotenuses. And there we go. That's what we wanted to show because therefore G is the midpoint. All right, so it took a while. It was sort of a combination of looking at similar triangles. I'm glad I noticed the parallel line stuff. And then getting rid of this triangle to turn it into these two triangles. And then it took me a little while to notice we got these triangles. The reason I saw that is sort of, I was trying to say, well, okay, yes, we've got all this, and we can play around with this bit, but how are we going to get up to G? Because that's the sort of important thing. We were playing around in an area that didn't have G. So I tried to extend my triangles out to include G. You might not have been able to jump straight to this triangle and this triangle are equal. You could have maybe done the big cyan triangle and orange triangles have equal area, which is what I was going to do until I realized I could jump all the way there with similar triangle work. Anyway, okay, so we've got one more part, C part. All right, given that the area of ABD is 4 and CBD is 6, compute the area of EFG. Okay. So we'll draw our big picture. A nice triangle there, parallel line. So A is here, G is somewhere on BD. These lines are still parallel. Oh, now EF is going to be our common base. Oh, this is a cool exercise. Anyways, B goes here, F goes here, E goes here, D goes here, G is here, and C is here. Now, you might think, well, they're talking about EFG. I better add in these lines here. And while you can, BD is the same constant height, H, that we had in part A. And so all I really need to do is compute something like DEF or BEF, and we're fine. Because it'll be this, it's the same height, same base, so it'll have to be the same area. So I might use that in a moment, but I still don't know where I can do my calculations. Okay, so we're told that this one here in blue was 4, I think. And then what is the other one they said? They said ABD, CBD, so the opposite side is 6. So this is 6. So the quadrilateral has area 10 is all they're saying right now. Maybe we'll have to use the fact that 4 is separate down here, but so I can say area ABCD is 10. But what did we just learn? We learned that these two halves, and they are halves of the quadrilateral, are the same area. So we can say by B, ABC has area the same as AC, or let's say ADC. Just to keep the A's and the C's in the same spots. It goes, and that'll be 1/2 the area of ABCD, so that'll be 10 over 2, 5. So each of these triangles has area 5. Okay, so that's a nice observation, but where can I go with that? Well, we could probably do some sort of... Oh, I do know we did just prove that these are the same length there. Whether or not I need that, I'm not entirely sure. We did go through the trouble to prove that. So... Oh, and similar to what we saw with the angles there, this angle here and this angle here are the same. And are we going to have, by the sort of Z parallel line theorem, this angle here and this angle here are the same. This angle here and this angle here are the same. So maybe I should focus on AEF. Because that's going to be sort of some multiple of 4 in a sense. And then, well, I guess if we just took something like, oh, I'm running out of colors. We found like BAF or something and figured out that area plus this area, that would get me the same area as G based on the parallel line arguments. So that's a plan, but how am I going to get the area of those two triangles? Okay. So if I want ABF, let's just focus in on ABF. Yeah, put G up here. Well, I'm gonna have to draw it a little lower than that. So A here, B here, F here, C here. Now I know that this thing has area 5, but we were also playing around with similar triangles a little while ago. I know that this area is the same as that other thing's area. D here, G here, so I know those are the same. I haven't found a place to use that. This area is the same as this area. I'm really not sure where to go. I probably need some other similar triangle somewhere. Or maybe I can go back and look at the similar triangles I've made and see if something's jumping out. But sort of, I want to say, you know, this area should be the same, because we have things like, what do we call it? This one would be I, because we had F here. And so we have this common height. And I know BF had a nice ratio with, has some ratio with CB. That's how we were able to sort of jump and do those similar triangles there. So this is, I think we called it R minus 1 BF. And so 5 is to the area of this thing. Now that's the problem. I can't quite... find the right ratio that I want. Hmm. Well, what if we go back and take a look at some of the other stuff? I think the... no. Maybe I should use the whole triangle, because I know this bit up here is not G, it's a 6. So is there a way for me to get the whole thing and then maybe work on the base, because then I know these two bits are the same. Is that helpful? Maybe the 5s I've got are misleading or something. Hmm. Or maybe I shouldn't be focusing on those bits first. Maybe I should be focusing on this triangle down here. Because it's similar to this one. I can definitely say that for certain. And so we get some nice ratios of sides. For example, AD is to AF as AB is to AE, and that sort of a thing. But does that really help? Because it's not like they have a common base, so I can't say... Well, whatever this ratio is, I could then... Yeah, if I could find the ratio of AD to AF, or AB to AE, or something like that, and it turned out to be S, so, for example, if AB over AE... Oops, other way around. AE is the one I'm scaling up. Is the scaled up one. So if I found out that was, say, we already used R, so let's say P, then triangle AEF, because it's similar to ABD, would have area P squared, because when you stretch all the lengths by a common factor, the area is stretched by that common factor squared. And then, oh, well, I know that this up here is 4. So that's something to look at. I'm not sure if it's necessarily going to go somewhere, but it's certainly interesting. So I can go back and look at ratios. Now, what ratio would we necessarily... I think we're not given any particular information one way or the other. So looking for AE over AB is no different than looking for AF over AD. The question is, where can I find these ratios in the wild? They're not exactly heights of anything. So... What on earth can we do here? Maybe if I drew a simpler picture and, focused on exactly this ratio. So let's ignore this area here. Ignore this. We'll add that in if I need it. So if I'm just looking for AB over A, or AE over AB, I suppose It's, I guess, the base of this slanted C, or this C triangle up here. And I do know that this half is 5. This half is 5. This is 4 down here. And then some unknown quantity ADE, which I still want to work out. And I don't know, we could call it Q for area. Well, let's make it a capital Q because it is an area. Nah, let's keep it regular, little q. This is probably the least of my concerns. Anyways, a little q there. If I extend this out, just as we did in A part, I can drop a perpendicular from C, wherever it may be. And then, oh, C, so triangle CBA has area, I don't know, call this H again, 1/2 HAB. Triangle CBE has area 1/2 H. Actually, no, let's not do CBE. CAE. CAE would get AE by itself. And I'll rearrange this to say AB. Oh, I already had that one as AB. Silly me. So then the new base is AE, and they're on the same line, because I know that's true. So the ratio of them is, so it's Q plus this 5 right here. I was about to say Q plus 10, but it's not the whole thing. So AE over AB, the ratio that we're calling P, is CAE, that triangle, divided by CAB, which would be Q plus 5 over 5. That doesn't exactly help. I mean, we've got two equations, or one equation and two unknowns, but it is our relationship. And I do need to work this Q out anyway, so I guess that's kind of nice. And then the baser triangle here is P squared 4. And so my answer, whatever my answer is going to be, is Q plus P squared, or plus 4P squared, eventually when we work that out. Now, is there another equation I can get here? Maybe not necessarily based on AE over AB. Oh, we could drop a perpendicular from D. Have a new height, I don't know, call it G. So, what are up to? We used K, so we'll call this L. So triangle DAE is 1/2 G, or we could call it DL, whatever you want to call it, AE. And triangle DBA, again, same base, I'm going to say AB. And that uses the 4 quite nicely. Is 1/2, same height, because it's all coming from the same point and the same base. And then AB. So again, P is AE over AB, and this should involve a 4, not a 5. And so it'll be Q, this area, over 4. And now I've got two equations. I can solve for Q, and then I can solve for P. There we go. So 5P is equal to Q plus 5. And then 4P is equal to Q. Subtract those. P is equal to 5. And so if P is equal to 5, then plug it back in here. Q is equal to 20. So now, finally, we say EF is common base to the triangle that they're asking to be about, EFG. And, I don't know, doesn't really matter. Use B or D, doesn't matter which. So I'll say E. Well, since I have Q labeled there, we'll use D, so EFD. But by A, EF is parallel to BD, and G is on BD. So same height. Therefore, the area of EFG that we seek is the same as EFD, which is, well, we'll move it on to the other side. So triangle EFG has the same area as triangle EFD, which we can break down into DAE plus AFE, I guess. And this is going to be Q plus 4P squared by similar triangles. I drew it earlier on when I was talking about these angles here. I verbally explained it, never actually wrote it down. But it's a quick thing to write down. AFE is similar to ABD. And so the areas scale up by a factor of p squared. But I know that this is 20 and this is 5. So we got 20 plus 100. So our final answer, at long last, and it has been a long question, is 120. There wasn't a whole lot of deep geometry. It was, to this question, it was just seeing the various similar triangles, common bases, same heights. I mean, that's what carried us through the whole way. But maybe I wasn't drawing my pictures in the right way to see them. But it certainly did take me a while, I think you'll agree, to see the right things. A part wasn't bad, but really hard to see the right triangles to be approaching in B part, although maybe there's an easier way. You can certainly see their solutions up online. And maybe they've got a very easy triangle to look at, or ratio or something. And then limiting myself just to looking at the nice AE, AB that I wanted. I saw this triangle and then eventually this triangle here, and that really helped. Okay. But there we go. So that's C3. Up next, C4. That is the very last question on our paper, so I hope to see you for that in the following video. Until then, take care.